Thank you for joining us for the morning sessions now for PyData Virginia. I would like to introduce our next speaker, Suhas Pai. Suhas is joining us from Toronto, where he is the co-founder and CTO at Hudson Labs, which is a startup backed by Y Combinator. He's also the author of the book Designing Large Language Model Applications, published by O'Reilly Media, which I think just came out. Is that right? Yeah, so it's hot off the presses. And he's contributed to the development of several open source large language models and is the co-lead of the privacy working group at Big Science. He's an active part of the machine learning community, and he's the chair of the Toronto Machine Learning Summit conference since 2021. And he's going to be talking to us today about making the most of test time compute in LLMs.
Thanks a lot, Patrick. Thanks everyone for joining. This is my first time in Virginia, and I'm enjoying every single minute of it. Patrick already introduced me, but before I start, maybe we could just have a vibe check. Maybe if you could have a show of hands, how many of you here have experience working using LLMs that use test time compute? That's models like DeepSeek R1 or OpenAI O3, O1, etc. So that's quite a few people. How about how many of you have experience training models for reasoning, etc.? There are plenty of hands up too. So the way I was planning to structure this talk, the first half of the talk I wanted to give a backgrounder, and the second half of the talk I wanted to spend some time discussing some of the experiments that I have made in the last 1 or 2 years working in this area. So let's start. So every week we see this that the leaderboards of all the major benchmarks, there's a new leader, and of course we know that the benchmarks can be gamed, and they are actively being gamed. But it's undeniable that the language models have been improving rapidly. Like if you remember how ChatGPT was in November 2022 when it first launched, it's so different now. So how can we make language models better? So there are plenty of options. You can invent a new model architecture. Let's say all the people in this room, we got $1 billion to build the next state-of-the-art model. We have all of these options at our disposal. We could, invent a new architecture, maybe better training dynamics, invent a new optimization algorithm, or maybe change the way the data is tokenized, or improve the training data. But what matters a lot more, the better lesson is that scaling, either in terms of data or model size, etc., that is for the last few years, that has been one of the most consequential forces driving model excellence. So recently, we have been seeing some signs of diminishing returns for scale, and this was also confirmed in the OpenAI podcast, where they said they are now more data constrained. One thing, I guess there is a misconception, or at least a disagreement in research circles about whether we have run out of data to train models or not. Personally, I think there is plenty of data that has not been touched and that has never made it into the pre-training data sets. What is happening though is that high quality data, or the data that actually is impactful, that is coming harder and harder to find, and also the amount of effort that you need to make in order to convert your raw data into data that is a lot more sample efficient is the bigger constraint. So one very promising avenue is the last one, where you think let's have the model as is, and let's try to squeeze a lot more performance from it. And that is by scaling test time compute, where you just ask the model, make the model compute longer in order to generate better results. So I'm not, I don't have a cognitive science background, so I think the analogies here might be a little dubious, but many papers have been trying to give this as an analogy that earlier the models that you have been working with are system one. um, they are fast, they output the answer directly. System two, you go through a slow deliberative process, you use logic and reasoning and then come up with the answer. So in this paradigm, like all the test time compute techniques are about system two, where instead of directly generating an output, we give the model time and computation to make it better. So, what are the different dimensions across which one can scale? It's two broad approaches will be parallel and sequential scaling. So, parallel scaling is when you generate for a given problem you generate n solutions, and that n can be as large as you want to be, as long as you have a good way to select the best answer out of the n. This was something at my company we were doing this for the last 3 years, or ever since we started using decoder style models, generative models, because if you are generating your sampling data um, from a distribution, there is always a chance that accidentally, the sampling process generated something bad that you just can't uh, recover from. So we always, for example, one of our uh, features was a summarization tool, and it needed to satisfy some very specific criteria. So we would generate five summaries and then use a bunch of heuristics as well as um, uh, transformer based models to decide which summary was better. So parallel scaling is that generate n solutions, select the best, and selecting the best today can occur either through using heuristics or even using reward models, uh, outcome reward models or process reward models, etc. Sequential scaling is when you just do one solution, but you have these verification steps, or where you either do it yourself, like in this case the LLM itself does self verification, or it relies on a verifier at every step in the process, and then it can do backtracking and so on. These are and then there is hybrid scaling that tries it uses tree based approaches, etc. If I just wanted to check, just hearing this, how many of you think that parallel scaling is a more promising? Uh, like you can just raise your hands, uh, or is it sequential scaling? So many of the models that we have seen recently are using sequential scaling, but there is, although for the proprietary models we don't actually know what's happening. There is some speculation that there is best of n happening in some of OpenAI's models, but it's just speculation for now. But on the scaling dimension, you can also scale at solution level or step level. So you can have n different solutions, or you can break down a task into several subtasks and then scale at each step. Um, the other dimensions that you could also uh, scale at the test time is test time training. Like what if during inference you undergo the model undergoes certain training for that is specific to that particular task, or in context learning scaling where you give different few short examples in the context. You give different examples in the context and try which of these examples would work better in order to give the output. Um, so scaling test time compute works. We and the This was from the S1 paper. As you can see, average thinking time as the number of uh, tokens that the model takes to come up to the answer increases. The performance on many of these benchmarks increases. But even if you use a model like OpenAI's O3 or R1, you can also vibe check and see that there is definitely um, a big lift that you get by thinking more. So parallel scaling, as I said, uses these methods. What I found was, you can use smaller models. So, for example, the best of n could uh, need not just be the same model being. Uh, you don't necessarily need to use the same model to generate it. It could be multiple models and so on. So sequential scaling, either you use external verifiers or LLM as a judge, where the model itself tries to verify what it's saying and then backtrack if needed. So what are the pitfalls with this? And now I'll go to the next part of the talk, where talk about some of the experiments that both from the research community and that I have done personally. So as you can see, this is a very simple question, and the model gets it right in like the first try. But what it does is it tries again. It instead of just outputting the final answer, it just continues thinking. It continues thinking and it verifies once, it verifies twice, it verifies three times, and then it gives you the answer. And you lost so many tokens here. This costs money, and so this is one aspect of it. So this is an easy problem. It got it right in the first try. But what if it was a more difficult problem? Then maybe it gets it wrong the first try, maybe gets it wrong the second try, but it gets it right the third try. But rather than giving you the final answer, it continues to think and then gets it wrong the fourth try. So it overshoots the solution. So this is the major challenge right now that is impacting the models, is how can you control the amount of time that you give the model to think, or how can the model itself self-regulate its thinking? How can the model stop where it needs to stop? And uh, so there are things that you can do on the training side, um, and I think I'll maybe talk about it later. But I'll first start talking about how we can do it from the consumer side. Like if we are using models, how can we do things that help um, um, help with uh, making the models more uh, attuned to how much thought they have to process for a given problem. So budget forcing is like one of the simplest solutions. So you can see that there are these tokens like weight, alternatively, maybe, etc. So if you look here, every time it starts, you know, a new step, it uses these words alternatively or wait or maybe. Uh, so what if you insert? So you set up a budget, and then when you see that you insert the word wait so that you can make the model think more. That's uh, the budget forcing technique, and this differs from model. So this is the output from DeepSeek R1, which uses alternate. So it depends on their post-training process. I think there are other models where the word alternatively doesn't appear as much in the thought process. So you need to find out for your model what are the those indicator tokens that represent the start of a new thinking step, and we just add that weight and then make it think longer until we pass a certain budget. Uh, you can also make it stop thinking if it's crossing the budget but it's not yet generating the answer by doing the end of thought token. Again, this differs by different models, and then putting final answer is, and then you are forcing it to do the answer. So this is a very basic way to um, to control thought. But the pitfall is that if you just add weight, it has the tendency to be stuck in repetitive loops. Imagine if you added weight here and it just continues doing the same process again and again. And again, yeah. Um, okay, so the other thing you can do, can we just prompt our way through it? Think for 2000 words, think six steps, think really, really hard. Does any of this work? So maybe in future they will work, um, and then you can just prompt your way through it. But as of now, it doesn't really. So you need to fine tune your model so that you can provide so that after you fine tune the model, you can use these prompts. And then the way to fine tune it would be like, okay, prepare a data set where you have these kind of prompts, and then you know you the reasoning trace in that data set would be following this particular instruction, and that could be done both from a reinforcement learning or supervised fine tuning. So um, an example of a reasoning trace. So this is how the data set would look like for the second one, think for six steps. So think for six steps. This is a one of the neater ways to control thought. You can say think for six or think for five, etc. Because models cannot count tokens. You can't say think for 2000 words and expect it to just think for 2000 words. So a more coarse-grained thing like think for six steps works better. And the way the data set looks, so this is how we prepared it. So we asked the model, so the reasoning trace contains, and you can see there, I have 3 steps left. I have 2 steps left. So the model is actually counting all the way to 0. And then when it counts 0, it outputs the answer. And then in your prompt, you can say, think for 10 steps, think for 3 steps. It can be, dynamic. But this is how you can, uh, prepare a data set for um, for making this prompt work and fine tuning that model. Uh, right now, if you use R1 or OpenAI, OpenAI has this parameter where you can reasoning underscore mode, I think, and I think that is using the third one where it is it's very coarse grained. It doesn't control the number of steps that you think, but it's just has maybe 3 buckets where it decides whether it's going to think for less or medium or more. Uh, and so the other thing that we can do is using critic models. And in this case, it's been seen that because for a lot of tasks, it's easier to verify than it is to produce the answer. Once you have the answer, it's easier to verify whether it's correct or not. So you can use smaller models that does do the verification, and then they provide feedback. And this, you can think of it as one very large model being guided by a bunch of very small models in order to get towards the final task. So what kind of feedback can be given? So it can be binary, in terms of a rank, in terms of a rating. It could be pairwise, but it could also be verbal. Verbal is like the easy way out, because we are just depending on the model to just output the feedback that it wants to give. But verbal may be a little harder to do for the smaller models. So how yeah, so how do we achieve all of these? A lot of it goes back to how creating very effective reasoning data sets. And there have been papers where they show, okay, you just use 1,000 examples and your model is now suddenly a very good reasoning model. Is that true? Well, it's true in a very, if you have to make a few assumptions. So, for example, the S1 paper that I mentioned a few minutes ago, they constructed 1,000 um, example data set, and they made a 32 billion parameter model uh, have a great uplift just with those 1,000 examples. But what really happened is that the model that they used was Alibaba Qwen 32B Instruct, which is a really powerful base model in of itself. So you can't expect, so for the reasoning models, or for any of this test time compute to work, the base model should already be very powerful. And none of these would work in models if the base model is not good enough, then none of these are worth it anyway. So that's why the other scaling dimensions are still important. So constructing data sets here, it will like uh, finding difficult examples, or if you are generating synthetic data, because it's very hard to get uh, manual data, construct manual data like this. So a lot of the time you would be generating synthetic data, but you can use a bunch of seed examples. But the seed examples need to be really good, and they need to be diverse. Otherwise, when you are generating synthetic data, you have a data diversity problem, and you are not covering all aspects of your problem space. In what we found, like I work in the finance domain, and we actually have financial experts do at least some of the training data, like manually, and even for the ones that are synthetically generated, every one of those examples at least goes through a manual inspection. So the other thing to also note is the difficulty. How easy is this example? Can you already use the non-reasoning model to solve this problem? If yes, then there is no need. Like you should not include what is 33 plus 45 in a reasoning data set. You should only include examples that are actually difficult for a model to do. Um, so yeah, so this is like the standard kind of train to think pipeline, where you use a language model to generate um, an answer, and then you generate two versions of it. One is where you use very little reasoning steps. One is when you use a lot of reasoning steps, and then the ones with lot of reasoning steps would be the positive examples, and the others would be the negative ones. Um, so finally, um, yeah, so these were very preliminary experiments that I'll probably publish more in a blog post later on. But it is interesting to see that when I take the first n tokens from DeepSeek R1 and then feed them to a much smaller model, the performance of the smaller model is much better. And also something with R1, I asked the model to think in Mandarin and output um, output the answer in English, it actually performs better on the more difficult logical reasoning tasks. So one of the speculations that me and my friends have is, the Shannon entropy for Mandarin is higher, or it's also the case that the data composition for of Mandarin in DeepSeek's dataset is much higher than it is for other models. So that's about it. And yeah, please let me know if you have any questions.
Thank you. Any questions about any of this from the audience? We've got time for a couple of questions. I was really fascinated by this last point of making the model think in Mandarin and outputting in English. Do you have any theories for why that might work?
Yeah, so as I mentioned at the very end, so one reason is the data composition of the training data of DeepSeek. Like OpenAI is also multilingual, but English forms a much more significant part of the data set. I don't remember the exact proportion, but I think for um, DeepSeek, maybe around 40% of their data was in Mandarin. So that's one of the things. One of the could be one of the reasons, but we are also thinking about how certain languages are they just more amenable for reasoning, and that's a very much open question.
Any other questions from the audience? I'm seeing a couple there in the back. Here, I'll run the microphone up to you.
So I think along the lines of the question that was already asked, so do these models like have translation baked into them? Is that how they can kind of think in Mandarin and output in English? And the other question is that a prompt that you feed to the model, think in Mandarin and output the response in English?
Oh, we just have one microphone. More running than I was expecting. No problem.
Uh, yeah, that's a great question. So I actually experimented with multiple prompts. So one was you ask it to think in Mandarin and then output in English. But the other one was I translate it myself, like using a different model, and then I input the the query, the prompt in Mandarin, and then I ask it to output in English. Um, at this time, what would happen is because the prompt was in Mandarin, the thinking would be in Mandarin, and then just the output will be in English. So I don't need to say think in this language, output in that language, um, and that produced better results because I can't control just by a prompt all the time. Think in one language and it's not responsive all the time. So to get the results, the best results, I had to translate it myself first.
One more question. Maybe I'll do the repeat the question thing, so I won't run the microphone this time. Yes, go for it. Yes. Was that the point that it was easier to verify an answer and harder to generate an answer, and why that might be?
That's a great question. So I think I said in many tasks. So in many tasks, it's actually not the case. So for example, any task that requires any slight amount of subjectivity, it's so for example, summary. It's much easier to generate a good summary than to verify it. But there are other tasks where it's easy. You can think of like cryptography; those are the canonical examples. But there are many other tasks where there is once you don't know how to get to the answer, but once you have the answer, you can say whether it's right or wrong. And the hope is that many of the problems that users care belongs to those criteria. But yeah, every time we run into those problems where subjectivity is needed, uh, that paradigm doesn't work much well.
All right, we'll need to leave it there. Thanks again. And we're having a book signing during the lunch hour. We have several published authors who are among our speakers today, and I think Suhas will be available during the book signing if you would like to check out his new book and ask any questions or talk more about any of this. I'm sure he'd be happy to. Okay, thanks again.